I took for granted that we had some, so I've got some temperature sensors up here. I took for granted that we had a heat gun over here because we're supposed to. And guess what I can't find? And I took for granted, then I said, well, I'll just use a soldering iron. Guess what I can't find? Soldering iron. So some of our sensors, we probably won't be able to see work with me. One of the things I did hook up the other day, and it was in our kit, in the little thing that I've got here, was a force sensor, a strain gauge. So what does a strain gauge do? That's what it does, but how does it work? So it's going to vary something, right? Every sensor that we have varies something. It varies its resistance with force, right? So the circuit that I have hooked up here, and I'll pass the strain gauge around and let you look at it so you can see the actual curls of wire going back and forth and back and forth and back and forth. So supposedly, if this is true, when I come up and put a force, so what I've got is, here's my strain gauge, which is right here. You could almost see it on the camera. Can y'all see the wires back and forth? And what we're trying to do is trying to generate a voltage. Now we could do this, we're using a Wheatstone bridge, but I didn't have time to set it up. And, so what I've done is I've come over here and got a very, very basic circuit. Where's my PowerPoint set? Well, undoubtedly I closed mine. Yeah. I'll just insert a slide right here. So what does it resistance do with weight? But it all depends, right? You understand that? So the way this one works, it goes down with force. So to develop the simplest circuit to develop an output with a sensor that changes its resistance is just come and put it in series with a resistor, right? So what we're using here is we'll use a fixed resistor. And what do we mean by fixed resistor? Huh? Yeah, its value doesn't change. And then we have our strain gauge. And I don't know the symbol for that. We need to look that up. But I'm just going to come up and draw it like that. And what this guy's doing is it's resist. And then I've got my meter hooked up right here. So this one R goes down when force goes up. When I press on it. So what should I expect the voltage to do? I got plus 5 volts up here. And I just grabbed a resistor. I got a red. What's that? Yeah, 2.2K. So what should we expect to happen, guys, to our voltage? Plus 5 volts up there. So what should we expect to happen on this thing when I come in and press it? Current goes up, but what we're looking at a voltage, but what we're trying to do is trying to figure out what's going to happen to the output voltage. Now the output voltage will go down. Now if I wanted to go up, I would just switch the resistor and the sensor, right? You understand that? So it depends on which side you put the fixed resistor. But if I press it, its resistance goes down. If this resistance goes down, current goes up, which causes my fixed resistor to drop more voltage, and my lower resistor drops less, right? You understand that? Okay. Because Kirchhoff's law says the sum of the voltage drops have to equal to the applied voltage. So here's my basic circuit. Here's my strain gauge, it's flopping around. And then here's my 2.2K. And then right now it's measuring 4.1 volts. And then when I come up here and just put a little force on it, what do we say? You can see the voltage drop drops, which means the resistance is going down, right? Everybody okay? See, if I put a lot of pressure on it, we can make it go to almost nothing. So what we're saying is if I can attach this to something and it generates a force, then we can use a voltage to give me a weight.
Slide the measure down. You're asking. Oh, I didn't see it.
I can't slide it down much more. This is the reading on the meter right here. Right now it's reading what? 4.9. So it's got a pretty good deal of resistance. I mean, and then I come up here and I'm just going to take it. And as soon as I start pressing on it, we see what? These things are really sensitive. Now, a load cell is a device that has two strain gauges. We know they use them in pairs. They're perpendicular to each other. And why is that? Yeah, one of them gives us a change its resistance proportional to the weight, and the other one compensates for the temperature of the resistance of the wire changing with temperature, right? You understand that? And then they put a Wheatstone bridge in there, and then they send an output out. And then what we do is we don't calibrate zero in the load cell, we calibrate zero in the gauge. Does that make sense? Yeah, we call it if you're familiar with scales, and even back the old analog scales. Now, of course, all our scales are computers. They got a microprocessor. I can make anything equal to zero with a computer. So I could get 50 volts in, and then I could tell, and it could go through my ADD converter, and it gives me a count out, and I say, well, that count is equal to what? Zero, right? So most your scales. So why don't they give us a thing? Because they have no idea. I mean, I might go out there and put a 50,000 pound load cell on a weigh bridge that weighs 2 tons, right? I mean, sorry, we couldn't do that because there was. But I could go out there and put a 50,000 pound load cell, and I have a 1,000 pound weigh bridge, or I might have a 100 pound weigh bridge. Well, if that thing gives me out a zero, then I'm screwed. Right, you understand? So what we can do is we can zero out the scale anytime. So that's the way we calibrate the scale. So the scale don't know what you're weighing. All it knows is I've got this. It don't know what situation it's in. So what we would do is we'd go out there and we'd when we fired the thing up the first time, we'd zero it out. It is a tare. That's what you're doing. That's what you're doing on your scale. You're taking your gross weight and you're taking out the tare is what they're talking about. But that's all you're doing is zero the scale out. And then we had calibrated weights. I think I showed you that, and we'd put it on the scale. And then we'd go in on the indicator and we'd say, okay, this is 10,000 pounds. And then we'd take it off again, because what happens is when you move this one up, it changes your zero reference. So what we have to do is, if you ever see anybody calibrate scales, is they'll go in and they'll put weight on there. They'll set it for whatever it's supposed to be. They'll go in and they'll take the weight off. They'll zero the scale again. And then I'll go in and put the weight on it. And that's the way they actually calibrate scales. Yeah, I was a certified. Suppose I was supposed to go to Montgomery and take a test, but they just gave me the license. So I've been blessed my life. They've done things for me they shouldn't. When I was in the Navy, they had something called a CID, which was a collateral duty inspector. And what those guys did is they checked the work of other people. And you're supposed to go through this long training session, and they just gave it to me. So I didn't have to go through all that. Thank goodness. Okay, so this is the circuit. So what I got, what I brought in is, we know we have temperature sensors, and I think the first one we looked at was a bimetallic strip. I have a bimetallic strip, but like I said, odds are we're not going to be able to heat it up hot enough. So anybody's got a gas furnace, and in the old days, you lived by the grace of God, but over time, they realized they have to meet a lot of safety standards on gas. I don't know, they just had a building explode. Where was that at? They just exploded. It was in downtown. No, it wasn't in Birmingham. It was off. And it's been the last couple of days. So natural gas is, it's a lot cheaper than electricity. But it's really, really dangerous, right? So any gas heater now has several sensors in it to make sure that we don't exceed what we're supposed to exceed. So we have these guys. Like I said, we probably won't be able to trip this because I can't get hot enough. We have these guys that y'all might have seen before, but you don't really know what they are. Don't let me do that anymore. So this is a temperature switch. And you can see it's got a flat side on it. And this is a switch, so it's set just to open at a what? Certain temperature and close when it's below that temperature. We run into these all over the place. Okay. And like I said, we could probably look it up and see where it trips at. We tripped it a few times, but we had to have a heat gun, or technically a paint stripper. You know, latex paint is basically rubber. And when you want to take it off, it's real hard because when you heat it, if you ever try to use sandpaper on latex paint, you just generate heat and it just smears all over the place, right? So normally what we do to take off latex paint is we have a heat gun and we heat it up and then we just scrape it off. Yeah. But it's hotter. Yeah, I used to smoke. I like my cigarettes off. We use it for heat shrink. Heat shrink is a special plastic that drops down to around a third of its size. This is the preferred method I'm looking for. I brought some in here. We use this for the preferred method for replacing insulation. So when we strip wires and solder them together, the preferred method is to use heat shrink, not to use black tape. Electrician's tape's nice, but the problem is it is held on by adhesives. And so the problem with adhesives is different things that affect adhesives different ways. I've got into circuits and the plastic tape was just brittle. It just popped off because it got in, and I've got it where it's untaped itself too because it got into a situation where it got into some type of chemical and it did what? It just ate the glue right off the tape. So the preferred method for replacing the insulation on a wire, once you've removed it for stripping or whatever reason you remove it on it, is to use heat shrink. So I brought a big old box in here. Oh, but you shrink it with a heat shrink gun, which is basically nothing but a paint stripper. In fact, when we ordered ours, we ordered it as a heat shrink gun, and we got them, and guess what was written on the side? Paint stripper guy. But they're really hot. So when I used to smoke, I used to light my cigarettes off my heat shrink gun. Just the air coming off of them was hot enough to light a cigarette. So yes, I did this. Quitting smoking was one of the smartest things I ever did, guys.
What you say, this came off of gas furnace?
Yeah, I came off my gas furnace. Oh no, what? Not that. What did I pass around? That just came out of some parts that we got. Look, you could use these things anywhere. This didn't come off my gas furnace, even though there might be one of them on there. We use these all over the place. And what we do is we trip out things. If you got a power amp in your car, I guarantee you, if you pull off the heat shrink, there's going to be one of those guys in there to keep from burning up your amplifier if you screw things up, right? You understand? If you got a clothes dryer, I guarantee you when you take your clothes dryer apart, you're going to find these things in there. Yeah, you trip it. You could have this thing on a relay. So, as long as it's cold, as long as it's below its temperature, the relay would be energized. If it exceeds the temperature, it'd kick out the relay, and the relay can control anything, right? You understand that? So these things are in all type of applications, but that's a temperature switch. This, huh?
Positive and common leads on it.
Only if you want to burn things up. It's a switch. We don't ever put a switch between positive and common. Normally what we do in between, that's DC. We're not dealing with DC in here. We're dealing with AC. Where do your control, so it is considered to be a control device. So where would it be, guys? Between L1 and the load. So here's L1. And then we would have, this is a normally closed temperature switch. So it comes up and goes on the top. And then this is the symbol of a temperature switch. And then over here would be our load. It might be a control relay. It might be the input to a PLC. But it's a control device. And a control device goes between L1 and the load.
So if it heats up, it opens.
Opens up wherever it goes. What?
Well, it has a temperature.
It has a trip temperature, yeah. It's a thermal. It uses a bimetallic strip. And what's nice about a bimetallic strip is depending on the two metals you use, you control where it trips at. So, and then it snaps. It's probably got a little plateau thing in there. I think we showed y'all that. It opens up. What's nice about these guys is that if they're good, then what happens? After they cool down, then you can do what? You can bring the system back up. So they're not in there to permanently disconnect something like, and they automatically reset. This gives us a problem. So motors over, I forgot what it is. It's really small, like a third of a horsepower. Motors have to be thermally protected. So what they do on a lot of motors is they put a thermal switch inside the motor. And the problem is it's a little bimetallic strip. And people will go out there and they're working on the motor's not working, and they don't disconnect it, and the dang thing cools off, and what happens? It automatically comes back on. So you gotta be careful of that. So if you're gonna work on a motor that's not working, you better do what? Yeah, disconnect. So this is a 3-speed motor. So how do we change the speed of an AC motor? I got a 3-speed fan in my top of my roof on the ceiling on about 3 or 4 of my rooms, and I'm flipping a little switch. By George, I'm not changing the frequency. Alabama Power gives me 60 cycles. If I was going to change the frequency, I would have to take AC, convert it to DC, and then use electronics to change the frequency, right? You understand that? So now that's one way. You're right. That's one way we can adjust it. And we can't use just frequency. So that's kind of misleading when they call them variable frequency drives, because if I change just the frequency, we're screwed up because of this guy right here. So X of L this is the amount of opposition a coil gives to AC. X of L is equal to what? Anybody know? Oops, sorry. Yeah, 2 pi FL. So that means if I want to speed up the motor, if I raise the frequency, then I screwed up, because now X of L of the motor goes up, it pulls less current, and the motor would stall. If I try to lower the frequency, then the current would go up and the motor would burn up. So on an AC motor, we cannot control the speed of an AC motor with frequency alone. So I don't like to call them variable frequency drives. I call them variable speed drives. what we do is we come up here and we look at the voltage. So if it's a 240 volt motor, and then it runs on, and it runs at 1700 let's say 1750 RPM. And then I'd come over here and I'd say divided by 250 volts. Then what I do is I come up with a voltage ratio. So if I change the voltage and the frequency exactly the same ratio, then I can control the speed of an AC motor.
I thought if you did that, then it would try to run at the speed and found out that.
What do you mean?
Like if you just put the proper voltage to it, it would try to run at 240, and that would probably work.
Well, no, because of current, what people don't understand is that we're dealing with power, right? You understand? So what happens is if I lower the voltage and the opposition goes down, then the current would be the same and would develop the same horsepower. In fact, some of these call these guys constant torque drives, because we can control the torque precisely, right? You understand that? So you're saying, okay, if I come over here and I have it's 750 watts per horsepower, and then that's at 240 volts at 60 cycles. Well, the problem is if I go down to 30 cycles, then I could come over here and put 120 volts on it and get exactly the same horsepower. Because what happens, voltage is going down, but current is going up, right? You understand? So we get exactly the same horsepower. So what we're doing here is we come up with what they call a voltage per hertz. Voltage per hertz. So I've got this backwards. It's 250 over the speed of the motor. And then that would give you volts per hertz, right? You understand? And if you maintain the volts per hertz, then what can you do? You can control the speed of the motor. But you just can't change the frequency, and you just can't change the voltage. If you change the voltage, then you're going to get big problems. In fact, once you get up to the maximum voltage, nothing happens to the motor, it just burns up. If you run it too low, with a too low voltage, the motor's going to slow down, but it's going to pull a lot more current. So you can burn a motor up by putting too much voltage on it or putting what? Not enough. But if you lower the voltage and the frequency at the same rate, so this is what you don't understand, is that X of L. So this is how much opposition the motor has to AC. Well, if frequency goes down, opposition goes down, current goes up. But if I lower the voltage, current stays the same, right? You understand what we're saying? So what we can do with a motor is with an AC motor, we can do what? We can control the speed, but we can't control the speed with voltage alone. And we can't control the speed with frequency alone, but if we change both of them, we can control it. So a variable frequency drive is kind of misleading because it's actually changing two things at one time, right? It's changing the what? Voltage and the current. So what you're saying is if I drop the voltage down, well, what you're saying is that this opposition stays the same, right? You understand? But the opposition does what? Varies with the frequency. So the opposition varies with the frequency. The actual formula is what? RPM of a motor is equal to what? 120 over frequency divided by the number of poles minus slip. That's the So if I don't change the frequency, what's another way I can change the speed? I can't change the 120. That's 60. That's 60 cycles. So how can I change the frequency? I mean, how can I change the speed if I don't change the frequency? Okay, if we're trying to figure out two ways we can control the speed of an AC motor. We can control it by using a variable frequency drive, right? Or we can control it by, how killing me, changing the number of poles, changing the number of magnetic poles. So that's why we got all these wires coming out of this motor. One of them would get us so many poles. The other one would give us so the less poles you have, the faster the motor runs, right? You understand? And all it is a matter of just rewiring the number of, y'all understand poles? Yes? No? Well, what we do is we come over here and a basic motor, this would be a two-phase, this would be a two-pole motor. Okay. Y'all understand? And it would have to go through 2 poles to make 1 revolution. So that's why instead of using 60, we use 120. The other formula is 60 divided by the frequency times the pole pairs. But they don't say a 2-pair motor, they'll say a 2-pole motor. If I come over here and add another set of poles right here, right, you understand? Then it's going to come over here and go through 1 AC cycle right here. If this is a north and this is a south, right? You understand? So that would be a 4-pole motor. So if I have a 2-pole motor, the motor would try to run at 3,600 RPM, but it can't run at 3,600 RPM, right? You understand why? Well, what happens, these are induction motors. So what we have is we have a bunch of conductors down here. And when this field comes up here and hits this thing, it induces a voltage into that field. What's the things do we need to have to induce a voltage using magnetics? Number 1, using magnetics. This is going to be on the next test. I'm not even going to tell it it's going to be on there. This is going to be on the next test. This question is going to be on the next test, and it's not going to be on the review. Yeah, it's going to be a 3 for 3. You're going to have to get all of them. What else? Got to have a magnetic field. Got to have a conductor. And we got to have relative motion. A lot of people say motion, but I like to use relative motion because we can move either one. Okay, so what happens is I come over here and I put 60 cycles on these things. It comes over here, 60 cycles, hits these things right here. It induces the voltage into it, a lot of current because it's acting almost like a short circuit. You ever seen the rotor of an AC motor? Creates a lot of torque. The motor pulls a lot of current because it's like working into a shorted transformer right now. Okay. Creates a lot of current. Then the phase shifts, and that's what causes it to start to rotate. As soon as the motor starts rotating, so I start off with 60 hertz or whatever it is. Then this guy gets up to 2 RPM. If he gets up to 2 RPM, then the rotor's only seeing 58 RPMs because it's relative motion. So when this guy starts spinning and this guy's spinning, so we're up here first, we're doing this, right? You understand? Then this guy starts spinning, and now the ratio of my frequencies on the rotor C starts going down because it's starting to catch up with my rotating field, right? You understand? So we come up, we have 60 hertz, and the motor goes up to originally 50 RPM. So that leaves me 10 RPM. So the motor's going to automatically start reducing in current, right? You understand? Because what we're changing is we're changing the what? The rate of the relative motion. Well, what the problem is if my motor got up to 60, then I have no more relative motion. I would not induce a voltage into my rotor. I would not create any torque, right? You understand? And the motor would start slowing down. So what happens is the motor's going to run at a reduced speed. So on an induction motor, the rotor cannot ever run at the same speed as the what? As the field. Because if it did, you'd get no what? You get no relative motion. If you got no relative motion, you get no voltage. If you got no voltage, you'd get no current in your rotor. You'd create no torque. So what speed are they going to run at? Well, they're going to run at a speed where the motor can develop its rated horsepower. So if it's a 5 horsepower motor, whatever speed that is, that's the speed it's going to be. So when you look at the speed of the motor, so if I look at this one, this is a 4-pole motor. So what would a 4-pole motor get? Should run at 1800 RPM, right? So if I look at the nameplate on this motor, this is not being recorded, it says it runs at 1725. I know it's a 2-pole motor because it's between what, 3,600 and 1,800, but it's gonna run at 725 if it's developing the horsepower that's on that label, right? You understand that? If you run it below that horsepower, the motor's gonna run faster. If you run it above that horsepower, the motor could do what? Not run away. The motor could stall. And if the motor stalls, it's going to pull starting current. The rotor's going to stop. It's getting the maximum in relative motion. It's going to pull a lot of current, right? Understand? So when I come up here on my ceiling fan, I'm changing the watt. I'm flipping switches. That's basically rewiring the number of poles. So it's a 3-speed fan. So I can go from 2-pole motor to a 4-pole motor to a 6-pole motor, which would give me what? Something below 3,600, something below 1,800, something below 900. So that's what you're doing on your ceiling fan. And if you looked at it, it's got a little switch that comes out, got 3 wires on it, and what's it doing? You're just changing the watt, number of poles. Now, how we got off on that, that's interesting. What I wanted to show you this is a 3-phase motor. This is one that's very standard in an HVAC system where we change the speed. They use a slower speed for heat than they do cold. Y'all know why? Because heat is lighter. Heat air is lighter than cold air. So cold air is harder to move. So they have to run the fan what? Faster than heat. When it heat, they run the motors slower. So here's our speed controls right here. I'd have to look at the color code. It's on the side. It's standard. This is where your capacitor goes. Your start capacitor goes. Okay. And then one of them's common, and then we have 3 wires where we select the speed. What I wanted to do is show you this right here. There's the 2 wires coming out. The other 8 wires, what do y'all think this is? Starts with a T. What are we lecturing on? Yeah, so this is a thermal switch right here. Now this gets a lot of air conditioning people hurt. The motor will cut out. They'll get their hands in there, right? Huh? Yeah, I'm telling you. They get their hands in there, right? You understand? Not killing the power, and then that thing resets itself. So these guys, a lot of times, by the way, guys, these motors they appear to be bad, and the only thing that's wrong is the what? This thermal switch. And you'll take it and trade it in. And, no, a thermal switch. These guys don't have thermocouples on it. Thermocouples are usually used in conjunction with something else. A thermal switch itself can just be put in a watt in the control section of this thing. So this just kills power. This just kills power to the stator. So this is, we call this guy here the stator. No, this is just where they connect the out. So this is the thermal switch. This is just where they connect the wires to the stator. So this is this is the field, by the way, but we call this the stationary field. So people call this the. So when we talk about the parts of an induction motor, we ignore the frame. You got to have a frame on the motor, right? And what does the frame do? It holds all the parts together. So they talk about the part on an induction motor. They say we have a field. So this is the stator. It's the field. And then the guy that goes in the center, we call this the rotor. And these are the actual magnetic poles right here. Now, don't count the number of poles because they'll use them in groups, right? You understand that? They'll move them in groups. So this gives us, I don't know if this gives us 3-speed on here or not, but I'll pass it around and let you look at it. So the rotor is nothing but it acts like the secondary of a transformer. It starts out by acting like a shorted transformer. So this might be the rotor that came out of the motor. And the gap is extremely close. In fact, they used to check it with like a credit card, a real thin credit card. So this is the rotor. So it's inside a set of laminated plates. And why do we use laminated plates for? To prevent, to make it act like a magnetic conductor and not an electrical conductor, right? You understand? And then here's your conductors right here. These silver bars that goes through here, usually aluminum. And these are actually shorted together on the end. So they have very, very little resistance until the motor starts coming up to speed, right? You understand? So technically, what we're doing, and I heard it called like that, is as it comes up to speed, the rotor appears to have more resistance. And if the rotor has more resistance, then the stator current goes down, right? You understand? It's just like a transformer. If I was to take the secondary of a transformer and short it together, if you was looking at the current in the primary, if you did it very long, it'd probably burn it up. But the current in the primary would be extremely high. Then I come up here and I start putting resistors in there, then the current in my primary is going to start doing what? It's going to start going down. So, and of course, when you start a motor, that's where you want all the torque, right? You understand? And then when it comes up to speed, you want the torque to go down and actually run at the horsepower we're doing. So this is the rotor. So in AC we call this the rotor, which makes sense. In DC motors, they're technically called the armature. The rotating part is called the armature, and the stationary part is called the field. That's what they're technically called. You hear people misuse those all the time. And then on an AC motor, this is called the stator. We don't even call it the stator field. We call it the stator. We call this the what? This is called the rotor. And of course, sometimes the bearing weighs out, and the rotor ever comes to contact with the stator. We got this problem. So that's the thermal switch. So we got on how motors work. I'm sorry we get off on that, but some of the things I think you'll really need to know, especially how a variable speed drive works. Variable speed drives are they currently dominate speed control of things. And why is that? Yeah. The motors are cheaper, not the electronics that run it. Well, what we was doing with DC, we'd have a motor drive, and then we would have a DC motor. DC motors are very expensive because they're wound rotor. When we went to AC, we had a motor drive, which costs about the same money, and then we're running an induction motor, which is a lot less expensive per horsepower. So this is why it took us a long time to be able to get the power to control AC. So what we do is we bring AC in, and the first thing they do is convert it to DC. And what advantage does DC have over AC? Well, I'm talking about DC in general. We can control DC electronically. So what we do is, what way a variable speed drive does, it brings the AC in right off the bat and converts it to what? DC. And then they re-oscillate it at whatever frequency they want. At whatever voltage they want, right? Because we can control the electronics. What advantage does AC have over DC? AC can't be stored. We can store DC. Can't store AC. So these big windmills that people see out there, they probably generate AC, but right off the bat they convert it to DC. And then they can store that in big old batteries, and then they can re-oscillate it, right, and convert it back into AC when they need it. Another big advantage of DC is we can store it. Can't store AC, but we can definitely store what? DC. And so what's the advantage of AC? It's not. I wouldn't say it was cheaper. One of the biggest advantages of AC is we can easily change the voltage. That's the major advantage right there. So we can step it up real easy by using transformers, right? You understand? Step it up real easy, just using a transformer, right? So we can step it up for transmission and do what? Step it down for safety. Very easy to do. Another big advantage, it provides induction. So we automatically have a change in magnetic field. So if we have a change in magnetic field, then we can use that feature for induction. So those motors that we're passing around, they're called induction motors, because that's the way you transfer power from the field that's spinning, right? You understand, to the what? To the rotor. It's done through induction. So the AC motors are cheap. DC motors are very expensive because on the DC motor, the armature has to be wired, right? It uses a lot of copper. Another thing about the AC motor is that it has no brushes. It has no commutator in there. So that means they last a lot longer. They take a lot less maintenance. DC motors, it's got that commutator and got those brushes in there that you're going to have to do what? Maintain. Okay, so the next device, I'm going to discard this and restart it. We'll look at is, what do we talk about? Bimetallic strip. Everybody okay? Thermocouples. So it's becoming very popular. The problem we have with thermocouples, but it's been taken care of a long time ago since we came out with computers. So computers can do things. So we know when we first look at our thermocouples, we got several ways we can establish what we call a cold junction. So basically, thermocouples requires what we call an active junction. Most people call it a hot junction. And then we have to compare that to a reference junction, which got the name cold junction, because originally it was actually put in a cold bath. But what we've learned over time is how to simulate the cold junction, right? You understand that? So most of our thermocouples now don't require a cold junction. We simulate the cold junction. What's nice about electronics and about a computer is that we can establish that reference electronically, right? You understand? So this is a thermocouple. This came with my Fluke meter. This is becoming very, very popular on meters as an option. So you see a lot of meters that will measure temperature. So this is a thermocouple. It's a type K thermocouple. Now what does the type of the thermocouple tell me? Can y'all see the type K? Y'all probably can't. Y'all see it when I pass it around. There it is. Can y'all see the K? So what does that tell me? Type K thermocouple. Tells me the range, and it also tells me the metals it's made out of. So here's our type K. This is actually one. So it's nickel, chromium, and nickel aluminum. That's the two similar metals. And it has a range of minus 200 degrees to 1250 degrees centigrade. God, that's hot. I doubt if I would ever get my meter that close. And so what we've added, of course, these meters will do all the math for you. They compensate for the junction mathematically through the processor that's inside the meter. So one of the ranges we'll have now, of course, when we look at these meters, is we'll have a temperature range. So that's where we measure temperature, right? And you'll see where I got it. Okay. And then, of course, we would remove our leads, and then we'd plug our thermocouple in here. What did I do? I give y'all my thermocouple? Maybe I should. How does it work? That's maybe the way I should have. Maybe the way I should have worded the questions.
Producing a proportion of close to EMF.
Yeah, produces an electromotive force, right? That's proportional to the what? Temperature. Everybody okay? Well, these guys don't have to be powered. So when I use a temperature switch, controls power, but all the other sensors we have to basically be externally excited, right? You understand? These guys don't have to be. All we got to do is make sure we honor the connection. I'm just going to connect this up to my meter. And then we'll turn it on, and now this thing should be measuring temperature. So right now it's measuring degrees centigrade. I need to turn it over there. So it's 28 degrees centigrade. Of course, so we should be able to make it measure Fahrenheit. So this is Fahrenheit. So it's kind of warm in here, right? So all I need to do is just come up here and touch it. And we should see the temperature start doing what? Going up. Now it's upside down. I'm sorry. We see the temperature what? Going up. So we use these things a lot. They're fairly accurate. They're not extremely accurate, but 90% of the time they're accurate enough, right? You understand that? They do have a little arc. They say they're non-linear. So when we talk about linearity, we're talking about things moving in a straight line. So if it was totally linear, then it means it would have so many volts per degree, right? You understand? But if we actually look at the chart, I don't know if this PowerPoint has a chart for a thermocouple or not, and this is not exactly true. This is out of a book. Here it looks like they're perfectly linear, but if we came up here and actually looked at them, they would have just a slight arc to them. But they're really good for where we work them at. So normally we can use them depending on where we're at, right? You understand? And also the nonlinearity, if we run this into any type of computer type situation, the nonlinearity could be compensated for by programs, right? Everybody understand that? This is not a good slide because here it shows they're perfectly linear over their range of 50. So according to this, I could come over here and say 20 millivolts. I could pull it over. It would be a little over between 500 and 1,000 perfectly, right? And that. So this is just an XY graph. I'll try to get a more accurate graph, but this right here is pretty close. The next one, I don't think we're going to be able to demonstrate, even though we got one. What determines the resistance of a metal conductor? I think I'm going to put that on the next page too. What it's made from, right? The size of the conductor, right? How big it is. So the bigger it is, the less resistance it has. Third thing. Now the length of the conductor would determine its resistance over length. And what's the fourth thing? Now that's what we're studying too. So technically, that last thing says we can use wires as temperature sensors. And they use what we call a positive temperature coefficient, which means its temperature goes up, their resistance goes up, the temperature goes down, their resistance goes down. So good, guys. What type of material from which the conductor is made, the size or gauge of the conductor, the length of the conductor, and the temperature of the conductor. Everybody okay? So what we can do is this guy right here. We can use it what? To measure temperature. Resistance temperature devices, RTD, uses a metal, platinum, nickel, and copper, increasing resistance proportional to temperature. usually consists of a fine gauge wire wrapped around a ceramic rod. I have seen film where they'd actually just put a film of metal on there, but those are not as good as the wire wrap. Very accurate and very stable. Of all the temperature sensors that we have available to us, this is the guy that is the most accurate. Yeah, because the best ones use platinum. Platinum's not a cheap metal, right? Copper doesn't work as good. It doesn't have as good accuracy. It's still really good. But the metals that we use, platinum, nickel, and copper, all these metals are not cheap, right? Reasonably wide temperature range. They're expensive. They require external excitation because they vary their resistance. A small change in resistance over its range of operation. So these guys vary in shapes and sizes, but basically, they can work in extremely harsh environments. Thermocool couples can too. We have the next guy we're going to talk about called a thermistor. You got to be careful with that thing. You can crack it and break it. Well, not really. But these guys can work in really harsh environments. We just seal them up real good, right? So we just have these things. This guy screws in. It's enclosed inside probably a ceramic rod or something that transfers heat real good. We take the wire, wrap it around a metal ceramic conductor. When that thing heats up, its resistance goes up. When it cools down, the resistance goes down. We can put that thing, we can make it generate a current with electronics. We can make it generate voltage with a resistor. Just as a resistor in series. So this is the one out of my firebox, and this is one I did. It's got two things on here, and we could probably make them work if I had my heat gun or if I had a soldering iron. And I'll try to remember bring those in because I took for granted that we had some over here. So this is the temperature sensor that came out of the firebox on my last HVAC system that I had. And it's got two things. It's got a bimetallic strip right here that actually warps with temperature. Oops, I just broke it. It just popped off. But it's got a switch back in here. It's kind of a limit switch, so when we torque it too much, it trips. And then here's the RDT right here. All it is just a bunch of wire moved around a rod. That's all it is. And then we come over here and one of these outputs would give us that. I tried to make my thermal strip trip, but actually knocked it off its little adjustment right here. This is the calibration for the strip right here. It's pretty neat. So like I said, I'll come in and if I can get my heat gun, I'll come up and heat these things up and we can see when they trip. So you're looking at two things, right? Here's the RDT and here's a bimetallic stripper. It came out of the firebox on a gas heater. So it actually stuck into the box. Well, one of them, the bimetallic strip, and I'd have to look at the control circuit. I don't have the print available. The RDT would give us an analog output of the temperature. But the bimetallic strip is set up so it trips a limit switch. So it would be an upper range. So it would work basically the same as one of these guys right here.
So the bimetallic would actually trip it. The other one would actually kind of change.
Tell you what temperature it was. The temperature inside the firebox was. Yeah, our heaters are becoming more and more complex. You know, the more they do. In fact, even motors. Blower motor went out on my air conditioner, and I went out there and I was looking for the relay that switched the speed. And basically, even though they use 3-speed motors, they only use 2 of the speeds. They use one for heat and they use one for cold. And what they used to do is switch it with a relay. So originally they switched the speed with a relay. Now they have solid state motors they put out there. And all they do is, it's got leads coming out and they put 26 volts on the lead they want the motor to run at. Even though it's a 240 volt motor, they control it with 26 volts. So it's an electronic motor. And that's what they're going to now for some reason. I don't like them because I'm on my 3rd motor.
But when you switch from cool to heat, you switch the lead.
Yeah, well, you're switching the number of poles. So you go from whatever they use. I think they use high and medium. They don't use low. So you're switching from 3600, and I'm saying it's going to actually be lower than that. You're switching from a 2-pole motor to a 4-pole motor. And so in the wintertime, in the summertime, you'd use, with your air conditioner, you'd run it at a higher speed, right? Because you're moving heavier air. In the summertime, in fact, heat air likes to move itself. You know, heated air automatically moves what? Up, yeah. So,
yeah, I got confused now. Something I was thinking about direction.
no, we don't ever change direction. What we're doing is changing the speed. In fact, the motors that we use in HVA systems, you can't change the speed on. Their speed is fixed. So the way we change the speed of an AC motor is we have to change the relationship between, we have to change the direction of the rotation. And on a single phase motor, what they do is they change the connection on the start winding. And some single phase motors are reversible, but the ones they put in your HVA system, they're not. In fact, my old unit that this thing came out of, the blower on the evaporator went out on it. And I found one and I put it in there, but guess what? It ran in the wrong direction. So instead of pulling air in through the evaporator and blowing it out the top of the unit, it was sucking from the top and blowing through the evaporator. And I ran that thing in there for, good gracious, probably 5-6 years before it finally went out on me. And the guy came out there and said, man, I don't know. He said, do you know your fan's blowing in the wrong direction? But the mixer, a semiconductor resistance varies with temperature. These are non-linear. Non-linear characteristics can be compensated with electronic devices. These guys are highly sensitive. They change their resistance a lot relative to temperature. They're very inexpensive. So we'll look at Jameco and see what we can buy these things for. And they're reasonably accurate. So most of the time, if we limit the span, they're really accurate. If we run them over their entire range, then they're not that accurate. So these thermistors, we use them all over the place. They're cheap. And I believe I can just modify my circuit over here just a little bit. So this is the way we, I should have took the figure number out. This came out of a book. So this is the actual curve to get out of the typical thermistor. If I tried to operate it over its entire range, it would be a lot of compensation, right? But if I come over here and try to operate it over a limited range, say right here, between 100 and 70 degrees, then it's pretty what? It's pretty linear. So odds are this is the guy that's used in the thermostat in your house, because your house, you operate it over a limited range, right? You understand? Very few would you ever run your house at 100 degrees, right? So usually you're in a very limited range that you run it in. So it becomes pretty accurate the smaller the range that we work in. But since it varies its temperature, since it varies its resistance, we have NTCs and PTCs. Don't know that. Negative. What does the T stand for? Temperature coefficient. So NTCs, these guys are thermistors that vary, whose resistance goes down as temperature goes up. A PTC would be a positive temperature coefficient. These would be the guys whose resistance goes up as temperature goes up. By far, NTCs are the most popular, and that's all we got up here. So these guys are real cute. They're basically, their size depends on the, and they look like capacitors. So here's ours right here. And basically the size determines how much power they're going to have to go. It's just like the size of the resistor. So normally the more power that a resistor's got to handle, the bigger it's got to be, right? And so that's what we do on a resistor. Over time, you learn the wattage by just looking at the size. So I can just about pick up a resistor and look at it. I know if it's a 2 watt or a 1 watt or a half watt or quarter watt just by looking at the size and not looking up the actual. Of course, you wouldn't know the number anyway. So this guy here varies its resistance. So we'll put in, if we want to make it develop a voltage, since it's an ETC, it's going to operate the same. So I'm going to come up here and put it in. I took out my strain gauge. Here goes one. Here's the strain gauge. So y'all can look at those wires moving back and forth. So let's swap. I'm gonna swap it around and make what we normally want to do is we want the voltage to go up when temperature goes up, right? So what I'm gonna do is I'm gonna come up here and swap that. So to make my voltage go up when temperature goes up, what I'll do is I'll apply the power to my thermistor. And you'll see my circuit over there. So I've got my 5 volt supply going to one end, and then I'll come up here and put my resistor in series with that. And if you rewire the circuit with power on, I'd suppose that's right. Then I'm going to come up here and hook my meter back up. And so this guy right here, it should vary its resistance, and it does it. It's really, really fast, and that's one of the advantages of these guys, is it varies its resistance pretty fast. Yeah, this is NTC. This is all we have here. We don't have any. And by far, the NTC is the most popular that we're using. So I have basically this circuit right here. I'm not using a 100 ohm resistor. I'm using a 2.2K. So that way I know I really protect this. So I've got my thermistor first. And then I've got my fixed resistor second. So if the resistance goes down, the voltage drop across this resistor will go up, right? And we're taking our output across that resistor. So now the voltage should go up when temperature goes up. Everybody okay there? Yeah, because it's an NTC. So what's happening? Oops, put it on DC. Still not working. So what's happening is that if this resistance right here goes down, Kirchhoff's voltage law says that the sums of the voltage drops have to equal to the applied circuit, right? So what happens when the temperature goes up on this guy, since it's an NTC, then R goes down. If R goes down, then RT goes down. If RT goes down, then IT goes up, which is going to cause this resistor right here to drop more voltage. It's going to cause this guy right here to drop what? Less. Everybody okay? We're taking our output across this resistor right here. So if I'm taking my output, so this is where I have my meter. If I'm taking my output right there, if its voltage drop goes up, then my meter reading is going to go up, right? If the voltage drop goes down, then my meter reading. And it's not working. It might be because of the scale of this meter. Y'all guys go ahead and take a break and let me figure out what's going on here. The problem we have with these guys, these are called clamp-on ammeters. And how do these measure current? They don't measure current. They measure the strength of the magnetic field. These guys are normally not intended to get into electronics, things that require precision. So these guys are not designed to measure millivolts and stuff like that. They usually measure volts. So you notice when I had it on DC, it only gave me 1 decimal point. Okay. And so the problem is the thing was changing, but the meter just didn't have the resolution. And what's resolution? Yeah, preciseness or accuracy. So it didn't have the resolution to measure that. So I went in there and got my digital multimeter. This is a 2000 count meter, which is on the low end on the resolution, but it still works great. And all I'm going to do is I'm going to come up here and touch my thermistor. Guys, I don't know what's going on. I mean, it was working perfect before y'all came in here, right? We should expect the temperature, we should expect the voltage to go up. There it goes. Also, what people don't understand is these leads right here also will measure voltage. It's still not working the way it's supposed to work. And you also have to compensate for this guy itself because it's a resistor, and what happens to resistors when you put current flow through them? They produce heat too, which gives us a little problem. So guys, I don't know what's going on. I'm looking for my other one. I mean, it was really good while ago. When I went and got the other meter. See, it's what? It's going up. It's going up in millivolts. That was the problem the other one had, right? You understand that? And also, guys, this is the main sensor right here, is these leads right here. So I can also come up and just touch the leads and notice the temperature starts going what? Should start going up. Do that. So the length of the leads, you got to be very cognitive of that. And then also, especially if they're different temperatures. But this is why my other meter didn't work, because it showed me 1.0 volts, and I was actually down here in the millivolts, right? Understand? This is a thermostat. Like I said, the leads are really, really good temperature sensors also. So what you'll see on this, so this is an old thermostat that I took out of my house. It's an old digital thermostat.
Right. By its measuring in millivolts like that makes it resolution higher, right?
Well, not necessarily higher. It's the resolution is the change.
Right.
The change. How much does it change? And of course, thermistors have a really good resolution. But what we would need to know is how many ohms did it change per degree. So that would be the resolutions, ohms per degree, because that's what we're going to, right? Ohms per degree. Yeah. So the smaller, yeah, the more ohms per degree it is, the higher the resolution, right? You understand? The less ohms per degree it has, the worse the resolution. So one of the advantages of thermistors is they have a really good resolution. Their resistance changes a lot with a small temperature change, which means it makes it easier to measure. This is the thermistor right here. So of course it's got to be opened up to your house. So any of your thermostats that you use on your house, you'll probably notice they got a lot of holes in the back because that's where it actually, the temperature it senses at. And so here's the thermostat mount, here's the thermistor mounted right here in the hole. And you'll see it's got a bunch of copper coiled wires around it. So that's basically, it's the leads are the primary temperature sensor on these. Are we okay? A little, yeah, well you can see them a little better when you look in there. You can actually see the reflection of the copper in there. And what they've got is they got a bunch of it out there to make it, the leads. So you can imagine it transferring. So we take the little thermocouple and we put ceramic around it, which means it's breakable, guys. So, you know, if you hit it with anything, you could damage the thermocouple. So these guys are not near as rugged as thermocouples. Thermocouples are very rugged, right? And also bimetallic strips, are they rugged or not? Well, you can do what I did and literally do what, bend them. And if you bend them, then you basically lost the calibration on them. So those you got to be really careful about, you know, putting pressure on it, just like I did.
On the thermistor, you just it went up in millivolts.
Well, it went.
It decreased.
Yeah, because of the way I wire it now. Because what I would say is, most of the time, what I want to happen is I would like my voltage to go up when temperature goes up. Don't that make sense? So what I did is I put my temperature sensor above the resistance. So what happens is when this resistance goes down, current goes up, the voltage drop across here goes down, and the voltage drop across here goes up. I'm taking my voltage across the fixed resistance. So this is a negative temperature coefficient, but the way we arrange the fixed resistor and the sensor would depend what happens to the voltage. Does it go up or does it go down? And it's up to you. So if I put the resistor on the top, then the voltage would go down as temperature went up. If I put the resistor on the bottom, then the voltage on the sensor. But these guys have to be externally excited, right? You understand? Because they don't give us a voltage, they vary their what? They vary their resistance. And I can't bring resistance into a controller. I got to bring one of two things. I got to bring a what? Current or a voltage. And of course, the most popular is a voltage. And it's a very simple circuit to bring that voltage in. You just put it in series with a fixed resistor, right? It could, but what you would do is you'd make sure that it's big enough so when you're operating this thing at its maximum temperature, you don't burn it up, right? Because it's going to be rated at a wattage rating. And plus, the more current you let go through it, the less current you go through it, the less the circuit is going to be susceptible to electromagnetic interference. Did I say it right? The less current you have in a circuit, the more susceptible it is to interference. The more current flow you put in a circuit, the less susceptible it is, because it has a real hard time for electromagnetic interference to generate a current, right? You understand that? So it all depends how to size that resistor. And also it would depend on the voltage range that you want out here. So the best I could possibly do, which you'd never see on this one, would be 2 volts. On a PLC, the lower the voltage is, the worse the resolution. So most PLCs use like a 10-bit analog to digital converter, which means we will take that input and we would split it into 1,024 steps, but that's into 10 volts. So if I got 10 volts, I get 1,024 steps, right? You understand? If I go to 5 volts, then I'm only going to see 512 steps. So what you want to do is you want to try to run your circuit as close to the range that your device is looking for. Does that make sense? Yeah. So most PLCs use 10-bit A to D converters. But that depends, it gives you the full range if your analog signal goes up to 10 volts, right? If it don't go up to 10 volts, then you only get the maximum counts within that range. And that would be the size of the resistor. So what we'd have to do is we'd find the chart, and it would give us the resistance of the thing. So normally they don't give you this for a thermistor. They'll give you about 10 different temperature ranges. And then it would give you the ohms for that temperature. And then what you could do is if you wanted to do this, then you could put dots on the thing, and then you could just connect the dots, and that would give you the actual arc on that. And then you would know, okay, what voltage dot, what size resistor I want to put down there to keep from burning up my thermistor, right? To get this voltage out that I need. So we might, if I needed 10 volts out, I might power that thing up to 20 volts. Because my maximum temperature might be right here. And if I powered it with 20 volts, the only way I would get 20 volts is to get 190 degrees, right? You understand? So it all depends on what size of resistor you use. Depends on the application of the resistor, what span or what range do you need. That's a good question. Any more? So everybody's seen it. Have y'all seen it? Infrared, know what infrared is? What is it? You're talking about the sensor, but what is infrared? It's a light. It's a wavelength, right? What's unique about, so this is not you can't use infrared by itself. And what you have to do is you have to combine this. If you're going to measure temperature with infrared, it's going to be an electronic instrument that you're going to have to power up with batteries, right? Not a standalone sensor, must be externally powered. It's a non-contact sensor, which is pretty neat, right? Senses by detection of infrared radiation. So the amount of infrared that an object reflects. So anytime light strikes something, it wants to do what? Reflect out, right? And so if we generate the right colors, and especially white light. So white light has basically all the color spectrum in there, right? You understand? Even light's wavelengths that we can't see. What's nice though is the amount of infrared light an object reflects basically doesn't depend on its color, it depends on its heat. So the hotter an object is, the more infrared light it reflects, the less heat we have, the less infrared. So if we know that, if we can measure the amount of infrared light that's reflected back, then we can convert that to temperature. But it's going to have to be an electronic instrument, right? It can't be just an infrared detector. All objects emit infrared light that is proportional to the temperature of the object. Actually depends on the price of it. So you can get pretty cheap. You can go down a Harbor Freight and buy an infrared sensor. Because a lot of people in HVAC use that, especially in commercial buildings, because most of the time in commercial buildings, where they put your vents. So I remember the guys working for HVAC, they would have this thermometer that looked like one of these meat thermometers that you plug in and you put it in the oven. And they would literally climb up on the ladder and they'd put that thermometer inside the vent. And then they would measure the temperature coming out of the vent. And that would tell them a lot of things. Now you don't see them do that. They'll come in and take their infrared thing and they'll point it at the vent. Now the problem with these sensors is that trying to keep them from picking up stuff away from what you're trying to sense. So a lot of them, especially handhelds, will have a laser pointer on them. So you're not sensing the laser, you're using the laser to do what? To aim it. That's basically what you're doing. That's exactly what it is. Yeah, that's exactly what it is. So we can use infrared to measure temperature. What's nice is, but they're a lot more expensive because now we got to add a lot of electronics to be able to interpret. First of all, we got to receive infrared light, right? You understand? And at a real high wavelength. So Infrared is the lower wavelength. So infrared is on the bottom of the light spectrum. So it's down there, you go into red, and you get dark red, and you keep moving, and finally you can't see, our eyes can't pick it up anymore. So it's at a wavelength. Y'all know light travels in waves. Everybody understand that? Just like a sine wave in AC. And if it travels in waves, then what we can do, if it travels in waves, then there is a distance between these peaks. There's literally a distance. So Alabama Power, when it's transmitting 60 cycles per second, there's a distance on that wire between this positive alternation and that positive alternation, right? You understand that? Which is pretty neat. So this is what we call wavelength. And it's usually given in nanometers or angstrom. And I have to go back and tell you what an angstrom is. Infrared is around 710 nanometers. Really. But if you get into on the top end is your violets, right? Ultraviolet is up in the top end, and then infrared is down top. The hotter the target being measured, the shorter the wavelength. So actually what's happening is it's changing the color that it is. Effective emitting energy is thermal radiation, non-contact, and measure temperature of better watt. So there's a lot of these low light cameras that people use that use infrared. And that's what it's doing. So people emit a lot of heat, right? I understand. Surrounding areas like trees for very little heat. They can take that and convert it over to heat. So we got all these types of infrareds. They look a lot like optical sensors. So this is the gun somebody was talking about. Where you just point it. It usually has a laser coming out, so you can point it and make sure you're pointing at the object. Because if you're measuring something up there, if you're down just a hair, then you're going to be measuring the wall, concrete wall. And they're really sensitive. Yeah, and they're pretty accurate, but it all depends on the accuracy of the electronics that you put in there. So, in rule of thumb, and this is where it's true, is probably the more expensive it is, the better the resolution, the more accurate it is. But working on HVA systems, you probably could get by with a Harbor Freight. Are we okay?
Actually shoots out a beam.
No, it don't shoot out anything.
How do it know?
It's measuring the amount of reflected, it's measuring the frequency of the reflected infrared light that you're reflecting right now.
Okay. So everything has reflected. So
everything reflects light. Everything reflects light. And what's nice, infrared, the amount of infrared that reflects off you basically has nothing to do with the color of your skin or the color of the clothes you're wearing. That's all it is. And what we're saying, a lot of these guns will have a laser pointer on it, so you know that you're pointing at what you want to measure the temperature of. Especially if you're over a wide range, because people don't understand that. I'm off a degree right here, but then that error increases over time, right? You understand? So normally these guys, the ones that point would have a laser on it. These guys, you would have to line up yourself. I don't know how you would do that, but they come in all shapes and sizes and different sizes. This right here would actually be the sensing head. This would actually be an infrared transistor. But to actually measure something, I would have to add electronics to actually do that, right? Understand?
That other chart you have up there, you got to use some language. How far you can get away? How far can you get away?
No, this is reflective. This is reflective. Infrared runs between 720 nanometers to 100 microns. And that's the range of infrared. All that is the range of infrared light. What happens is that depending on your temperature, your body, your reflected light is going to change between this range.
That's what I was trying to decide, how far away, what's off, right? Somewhere between, like here and DFP?
I imagine it's all, I imagine it's line of sight. Because all you're doing is measuring reflective light. It's just that the further the person gets away, the more accurately you're going to have to point the thing. This guy can measure temperature thousands of feet.
Really?
Yeah, because all it's trying to do is see light. That would be like saying how far away can a person with a flashlight be, and you can still see the flashlight. How far?
I don't know, I guess, to the curvature of the earth.
That's probably right. And that's basically the way infrared works. But the closer the person to the flashlight is to you, you don't have to focus as well, right? It's like looking at stars. How far can we see reflective light? A star is nothing but what? Not stars. Our planets are just, most of our planets are not suns. It's just what? Reflective light. And how far can they be off? Well, the further they're off, the more accurate you have to be, right? So I can take a telescope and I can aim it at the moon real easy. If I want to aim my telescope toward Venus, then by George, I got to know exactly where Venus is at, right? Because it's so far off. And all it would take was just, you look at these telescopes where they measure this stuff, they got these real fine adjustments on them, right? You understand? So instead of sitting there holding them with their hands, they could not hold it and move it around. I thought my son's got an application on his cell phone. I need to get this really cool. So he can take his cell phone and put the camera on and start pointing around. It's the neatest thing, and it'll show him what planets are. And we was out there one day, and he said, "Dad, the space station's fixing to fly over." And we went out on the deck, and he says, "It's going to come up right over there." And he was looking at it on his phone, and sure enough, we saw it. Here it comes. It flew right over our head. I need to find out what that application is. It's really. So I came over, we was out at the ball field one day, and I said, "Well, that planet over there is real right. What is that?" And he just put that application and pointed his phone over there, and he said, "Oh, Dad, that's Venus or something." I'll try to find out what that is for y'all.
Let me ask you this then. Okay, it's the temperature sensor, right?
But it's not sensing temperature.
It's sensing light.
It's sensing light.
Right, that's my question. So couldn't this be used for like proximity or whatever? Could this tell because of the change in the light when the object passes in front of us? Like we use it on.
We could use it to sense motion. Well, it'd be hard to do to sense distance unless you knew what the size was at a certain distance. Yeah, you could probably do that, but you'd have to be able to calibrate it for the size, right? You understand?
Yeah.
That makes sense.
Yeah. I'm thinking we could just like you could probably use infrared, like on system line where you use maybe reflectors or something like that. You just use infrared and it'll know when whatever in front of the train, it can just signal out.
Yeah, I would, but you have to understand a photoelectric sensor that uses a visible light is a lot less expensive than infrared electronics.
Yeah. I'm just thinking
Yeah.
that.
Well, you definitely could use it to sense the motion, right? You know what I'm saying? I think most motion detectors use infrared sensors. We have to go back and look it up. I think a lot of the motion detectors, like the ones you have in your house, use infrared to sense motion. Are we okay? Good question, Tim. Then we run into solid state, and I brought one with me. I'll have to look up the circuit. I'll probably do this while y'all out. So we have an LM35, and there's different ones. These are just the ones that we looked at. This guy is designed to handle centigrade. And it gives us, so it's an electronic circuit. What it's actually using to sense temperature, I don't know. There's nothing in the write-up that says that. But these things are, what's nice about these things is they are linear because everything the sensor, even if it's using a non-linear sensor, it can compensate for it what? Electronic. So the LM35 it's calibrated for the Celsius scale, and here's our transfer function. This is what? 10 millivolts per degree centigrade. And it can actually, it's rated for full range. It can go from a -55 degrees centigrade up to 150 range. Suitable for remote application. It will give us this no matter what range you work it at, but you can actually power this thing anywhere from on what? 4 to 30 volts. Very easy to power this on with batteries. Right, I can use a lead acid, I can use a 9-volt battery. I can use a couple of D cells, right? Less than 60 microamps current drain. So that's how much the guy takes to operate, right? Low self-heating, 0.05 degrees in still air. Self-heating means when we power the thing up, and we put a current into the thing, it's going to generate its own heat, right? So we can't have electricity flowing through anything without it generating more heat. That's not true. Capacitors, so that is true. Capacitors don't generate heat because the current does not flow through them. It flows in and out of them. So capacitors don't get hot. So if you got a capacitor that's hotter than ambient temperature, it means odds are something's going on and it's got current flow through it somehow, right? You understand? The plates that broke down are dielectric. Nonlinear energy plus or minus a quarter degree centigrade typical. So these guys are pretty linear. But it's hard to have something that's perfectly linear, right? What we have is an LM34. So the LM34 is calibrated for what? Fahrenheit scale. But it still has the same resolution, 10 millivolts per degree Fahrenheit. Then operated between a -50 and 300 degrees Fahrenheit, suitable for remote applications. This guy, the minimum voltage we need to operate this on is 5 volts, but it could go all the way up to 30 volts. Pretty good. Less than 90 microamps drain current, so it don't take much to run it. And then it's got a pretty good, I think the other one had a better linearity, I think. A quarter of a degree, this is, so that'd be 0.25. This guy right here is half. So this guy's not as accurate as the we can get this thing in several different packages. So it comes in TO36. So TO stands for transistor outline. Transistors require at least 3 leads. But they've got to put that in some type of package where I'm a printed circuit board maker. They got to have a standard package. If they just go out and did their own things, then I would have to make a special board to mount their stuff, right? You understand? So what they decided to do, and I think it's JEDEC, the Joint Electronic Device Engineering Council. They're the ones that register packages, what we put integrated circuits or transistors inside, right? They came up with something called TO, which stands for transistor outline, but over time, these guys don't necessarily have to be transistors. Any electronic device can be put in a 3-pin. Any electronic device that only needs 3 pins can be put in one of these TO packs if they're small enough. So all we need on this guy is we need to power it up. So it needs a what? It needs a voltage source. It needs a common. And then there's my output of it. So it's a complicated electronic circuit, but it fits in 3 pins. So we can get this as a TO46, which is a metal case. This is not one we have. We have the TO92 case, which is a 3-pin device, but it's not a transistor. You also can get this in a surface outline. We can get a small outline. I'm sorry, this is surface mount. I think we can also get them in a dual inline package too. These are the 3 that this company makes. So this is the guy that we got right here. So when we look at it, it looks like a transistor. The TO92 case is a little old tiny thing, guys. We're in, of course, what happens over time, we get more and more precise with things. The size of things determines basically how much current you've got to handle. The less current you got to handle now basically determines the size of the wafers that we can put these things in. If you ever looked at a microprocessor, and I've got a picture by the way of some, we're talking about, good gracious, we're up in billions of transistors that they can put inside a microprocessor. Because inside the microprocessor, they're handling logic. They're not handling hardly any current at all inside the processor. So if they don't handle a lot of current, what can they start doing? Putting them close together, making them smaller and smaller. So the only place the microprocessor has to generate a current is on its buses, on its output pin. This address bus and this data. So that's where your driver's at. That's where your bigger transistors at, but they're still not real powerful because all the microprocessor generates is devices that need logic, right? They don't need a lot of current, they need logic. So they don't need a lot of drive, but they're still up in the range of, they've got billions of transistors. They're still up in around 75, 80 watts that would come off those, not because of the transistors are so big, it's just so many of them. And that's why when you see a microprocessor, they usually have a fan on them or something to help dissipate the heat. So this is ours. This is a little DO92 case. And this guy, so 10 millivolts, and the maximum it could do, according to our data sheet, would be, and it doesn't rate the current, guys. We probably need to find the data sheet and see what current that would be, because it's kind of misleading when you say 10 millivolts per, when you come up and you say 10 millivolts per degree centigrade. So we probably need to get the data sheets out on it and see what current that would be at, right? Because if you try to load it down too much, there's no way in the world it's going to give you 10 millivolts. So this guy would probably have to be used at a high impedance or a high resistance circuit. So we couldn't use this guy to run a load, right? You understand that? If we're going to use it, then we'd have to amplify it, which is what this slide is showing you right here. We used to design these amplifiers, and all this kind of stuff, very complicated. And then they said, well, why don't we come up with an easier way to make amplifiers? And when we amplify stuff, by the way, we're amplifying power, right? You understand? And we can do that by either increasing the amount of voltage into a load, or we can increase the amount of current. So then they came up with what they call operational amplifiers. These guys are really cool. I don't know how many transistors. I could show y'all the actual diagram of an operational amplifier. But this guy right here is so neat. In that instead of me trying to do a lot of design into the thing, all we got to do is just use a couple of resistors to set the gain and also the amount of input and output impedance. So this is called a non-inverting amplifier, which means you bring the signal into the plus. I mean, when this goes up, the output goes up. We also can wire these things as inverting amplifiers, which means when the input goes up, the output does what? Goes down in the opposite direction. So we can tell right off the bat what type we are, depending on where the input is applied. And then this right here is feedback. So this circuit right here, this input right here sets the gain. And it's a very simple formula for a non-inverting amplifier. It's the feedback resistor, which is this guy right here. This is RL. This is RN. And the formula is RF over RN plus 1. You set the gain. So all you got to do to set the gain is just decide what size resistor you're going to use. So for engineers, this was a lesson. Very fast. So right here, they're using a 90K because they want pretty high. They don't want to load the thing down very much. 90K, 10K, so it'd be 90 over 10 plus 1. So this guy here is 10. Is that hard? Is that neat?
Gain of 10 volts.
A gain of 10, but these are voltage amplifiers. So notice what I've done. Over here it says we had 10 millivolts per degree centigrade. Over here I would get what? 100 millivolts per degree centigrade. But this guy would have the ability to provide more current, right? Not only does it give us a voltage gain, but it gives us the current. These, if it's a little, I think they said a 741. 741, we can't get a lot of current gain, but we can get more than the sensor can put out. And then we have op amps that are high powered op amps. And so these guys, they're called operational amplifiers, but just about everybody calls them op amps. This has almost infinite input resistance. We have to calculate it. You use a big old formula. I forgot. So what happens is the signal basically comes in close to here. So this guy right here basically sets the input resistance of the operational amplifier. But it's not 10K because it's times a multiplier. It's a real big multiplier. So the advantage of a high input impedance circuit is that it don't require, it can look at voltage because it's not hardly looking at any current, right? You understand? The disadvantage of high impedance circuits, the advantage is they don't require much current, almost no current. The biggest disadvantage is they're susceptible to electromagnetic interference. But I'm not going to give you the formula, but what we would take is we'd take this resistor, we'd multiply it by a number they give us for the data sheet, and that would tell us what this guy right here is. The output impedance is set by this guy and this guy. So we have another thing. Y'all know what impedance is? No. Impedance, a lot of people use them interchangeably, but they're not the same. Resistance doesn't change with frequency. Impedance changes with frequency. Okay, you understand that? It varies with frequency. What we've come into, what you'll find out is that just about any AC circuit, they'll talk about impedance, even though it has no active devices in it. So to get the impedance, you have to combine a resistor with an inductor, you have to combine a resistor with a capacitor, you have to combine a resistor with a capacitor and an inductor. So impedance is a circuit that contains both resistive and reactive devices. But what you'll find out, just like me, there's no AC in this circuit right here. But normally when we talk about in a communication channel, it became the industry norm. When we talk about signals, we use the term impedance, whether it's DC or AC. So a high resistance circuit would be more susceptible to noise, electrical noise. A low impedance circuit would be less susceptible to noise, but it requires more current, right? You understand? So it would be hard for this guy to drive a load. But this guy right here can definitely input this guy, which almost requires no current at all. I mean, this guy would probably be way down in the nanoamps, right? You understand? To develop something over here that can drive a current, right? You understand? Are we okay? We can set a gain of 1. We call it a buffer. So that's what they're showing you here. So normally what we're going to do is we're going to take the output of our solid state sensor and we're going to hook that into probably an operational amplifier. And why? Because we can get a real high input impedance so it won't load down our sensor, right? Understand? And then plus we can do what? We can get gain out of it. Everybody okay? The formula for non-inverting is a little easier. The formula for an inverting is RF over RE without the plus 1. So an inverting amplifier, we would come up here, and its circuit would look like this. So we would bring our input into a circuit that looks like this. So we have to put a resistor there, and this would come into the minus, and then this would come back and feed back into this, which would be the plus. And this is RF over RN, and the formula here. So in electronics, for gain, we use A. AV would be a what? Voltage gain. Would be RF over RN.
So one you just drew was, non-inverted.
No, this is inverting. This is non-inverting. And what you look and see what the input comes into. So if it comes into the one with the P symbol, this is non-inverting. If it comes into the one with the dash symbol, it means that's inverting.
So it's coming in on.
Yeah, if we set the same gain on this one, so here I could use like 100K, and I would use a 10K right here, and then that would give me a gain of 10.
Yeah, but I'm saying that the sensor is right there.
Yeah, but the sensor would be right here. But what would happen on this one if the voltage goes up over here, the voltage would do what? Go down. Over here, if the voltage goes up, the voltage goes down. Now, the advantage of an inverting is that we can set the input impedance right here. So on an inverting, this guy, there's a lot that sets the impedance. We have to know that number for the op amp. We multiply it by that, and that gives us the input impedance. This guy, the input impedance is big. We're talking way up in the megohms, right? You understand? This guy right here, whatever impedance I want, I choose R1. If I need 75 ohms, I'd put a 75 ohm resistor. If I needed 50 ohms, I'd use a 50 ohm resistor. If I needed 1 meg, I'd use a 1 meg ohm resistor. So basically on this, we can use this guy to set the input impedance. We can use this guy if we need an extremely high impedance. Now, why do we need to set the input impedance? Well, the problem is people don't understand that every source of a signal, every signal source has an internal resistance or an internal impedance. And then what I've got to do is I've got to take that signal and I've got to send it over to a wire, and eventually we're going to run it into something that represents a load. Okay, y'all understand? So let's just say this guy right here has 100 ohm of worth of resistance, and we're going to do resistance because even though it's stuff. And I'm going to come over here and I'm going to put 3 resistors over here. So I'm going to start off with a 10 ohm. I'm going to start off with 100 ohm, and then I'm going to end up with 1,000 ohm. Which one, and this is where I'm trying to get my power to, right? You understand? Which one would I get more power to? If it was a 10 ohm, or is it with 100 ohm, or is it 1,000? When would we get the most power to where I'm trying to get my signal to? Who says 10 ohm? Who says 100 ohm? Who says 1,000 ohm? Huh?
100 would it be?
Yeah, that's what we're going to find out. And that's what we're talking about. So, but let's do it. So we'll use the voltage divider formula. It's real easy. So what's the voltage divider formula? VRX, so we'll call this RX, is equal to RX divided by RT, and then we multiply it by my supply voltage. So let's use DC instead of AC, because we've all had DC, right? So what do you want our supply voltage to be? We'll use 10 volts, so that makes it real easy. So let's start off. So my first formula, and then and we can do this with one big swing, by the way. And then I can come up here and, so what's the formula? What can we do? What's the formula for power when we know resistance? We got what? We got V squared over R. So this is the one we'll use. So basically we could do this in one whack. So what I'll do is I would start off with 10 ohms. So that my power is going to be equal to what? 10 divided by 110, right? Times 10. Huh? 10 ohm first, so that's where we'll go right down the line. And then once I get that done, I'm going to square that. I'm going to hit the square key on my calculator. That's what's so nice about using this formula. and then I'll divide that by 10 ohms. Everybody follow that? Did I lose anybody? So here's my calculator. I'm going to come up here and I'm going to say 10 divided by 110, right, equals, I'm going to multiply that times 10, equals, I'm going to square that, and then I'm going to divide that by 10. So we got about 82.6 milliwatts over there, right? You follow this? You okay? So my next one, I'll say my power would be equal to 100 over 200 times 10, right? And then we'll flatten. Because, yeah, it's over RT. It's over RT. I went right past it. So I would say 0.5, right? 1 over 2 times 10. That. And I'm going to divide that by 10. So I got 100 milliwatts. Then I'm not going to write it down over there. I'm just going to do it because most of this you can do. That's what's so nice about the voltage divider formula. A lot of them you can do real pretty easy. So I'm going to take 1,000, right? I'm going to divide that by 1,100. Okay, didn't go. 1,000, 1,000 divided by 1,100. I'm going to multiply that by 10. And then I'm going to divide that. Oops, what did I do wrong? I need to, instead of using my mouth, I need to use my mouse. So we got 1,000, right, divided by 1,100 equals that. Divided by 1,000 equals that. I'm still doing, oh, that's the fourth, I'm sorry. Times 1,000. Okay, equals 901 milliwatts. I'm sorry, 91.9 milliwatts, or 92 milliwatts. So when did we get our maximum power transfer? When the resistance of the load matched the resistance of the signal source. We call this impedance matching. So this is the advantage. And this is why your cable TV, if you go out there and you break your cable coming into your cable TV and you went out and got an extension cord and twisted it together and hooked it back up, your picture's going to be crummy because you screwed up what we call impedance matching. That cable has a certain impedance. I think cable TV uses 75 ohm impedance cable. You can't measure it because it's an AC opposite, right? So this is what's so nice about an inverting amplifier. Even though we get a phase shift through the amplifier, whatever impedance I need, I just use what? I use that as my input resistance. If I needed 75 ohms, I'd use a 75 ohm resistor. If I needed 1,000 ohms, I'd need a 1,000 ohm resistor. We cannot do impedance matching with this guy right here. So this guy would be used on single ended impedance. These guys would be used. So that's the advantage. All you got to do is figure out what to do about the 180 degree phase shift. But you can take the output of this amplifier, inverting amplifier, run it into another inverting amplifier, right? You understand? You get your back in phase. In sound, inverting the sound makes no difference. And plus the formula is a little easier. So what a PLC uses, it uses an optical coupler. So these guys are really neat. And like I said, did I show y'all that, or or am I gonna have to find it? I only brought one. What did I do with that? I think this is the last one, so I'll find it and I'll hook it up. So I'm not gonna hook up this circuit right here because my meter, most meters, I think this meter right here, you can measure the input impedance of your input resistance of your meter. Just put it on and of course on amps, this guy's got almost no input resistance, right? You understand that? If I put it on ohms, it's outputting a voltage. So what we're looking on input impedance is over here if I put it on the volt scale. So you can put your meter on the volt scale, then I could get another meter and look across my leads, and it would tell me the input resistance of these meters. These meters run between 10 and 20 megohms. So they're really high impedance devices, right? You understand? So I'm going to hook this circuit up, and I'm going to output directly from the output of my sensor, and bring it into my meter. So my meter is going to be a load. So that'll be almost like hooking it up to one of these guys. I think at 741, we calculated the input impedance on the 741 op amp, which is a pretty standard operational amplifier, and it was up in the gigohms for a non-inverter. So we're talking about a lot of impedance, right? Or resistance. It is a resistance, but like I said, normally, and this is just a trade, even though we use it wrongly. Normally, when we start talking about signals, we use the term impedance, even though it's technically no impedance in this circuit. It's technically what? Resistance. That's just the way to trade. Are we okay? It's just like a lot of people on the DC motor, they'll call the rotating part, they'll call it the rotor, in the stationary field, they'll call it the stator. Is that technically wrong? Yes, that's technically wrong, but if you do that, I'll fuss at you, but if my boss did that, I would say, okay. I think that's it on temperature sensors, guys. We already looked at the different scales right off the bat. So here's our 4 different scales. We have the what? Celsius scale, we have the Fahrenheit scale, then we have the Kelvin scale, which is, it uses the same mark spacing as Celsius, but it's relative to absolute zero. And the Rankine uses the same marking scale as the Fahrenheit scale, which is relative to that. Any questions? All right, guys. What are we gonna do now? Go lab, and I'll find my LM34. There's no telling what I do with it. You know, hook up that. And when I get it hooked up, we'll come back over here and look at it. Oh, I didn't want to do that. Dang, Rich. I had it in my hand. Did I show y'all that? Did I show y'all on the camera before I got this? That guy's gonna be hard to find too. So Anthony, what lab are you working on? Because you missed some days, right? And since it looks like Jackson might not be coming back, what we'll try to do is split your group up and put one of y'all with Gary. So instead of, They are? Yeah, so.
Yeah, we on line 3. They still working on that.
Okay. Gary, Eric is gonna be your new, partner. So y'all can partner. Huh? Huh?
I'm sorry for Eric.
Well, it don't look like your other partner is gonna come back. I sent him a text, but he never has answered me. And if he does come back, we'll just stick him with somebody else, but it's not really fair for you to be trying to do this on your own, right? And it's not really fair for that team back there. It's not fair for the team back there to have to work with 3 people too. The more people you have, the longer it takes y'all to do laps. So I don't know if y'all notice that.
Yes. I'm trying to draw a diagram of what we need.
What's that? Sometimes you have, I think that's when you got to tap on the end.
Let's see what you got.
Okay, guys, I need to find my temperature sensor.
Here's the time.
Sometimes I get so frustrated.
Let me call up and let you take down. What we're doing, we don't need we need time.
I think you already got your timer up there. Is that your circuit? Gary?
Yeah, we got it.
Timer's already up there.
Yeah, I didn't realize I stuck it up there. And what I was going to try to do is try to get some points that put it up on the door with the short wire.
Yeah, guys,
I'm just joking, I know that.
yeah, we need to discuss that. Y'all come back, and if you made this mistake, don't take this the wrong way, because several people make this, and this is something we really, really need to teach. Is wire management. The problem we have is if you jump these things all over the place, it makes it extremely hard for me to figure out how you wire. So what we're going to do from now on, only one connection to the transformer. 2, right? I'm sorry. We don't double up on the transformer. And what I like to use is when you go and look at your circuit breaker in your house, you've got one wire going to it, right? And you got a common. So one wire, and what we want you to do is we don't want you to, so this happens all the time. I mean, it's something, and I can understand why, because of the way most people wire stuff, is I'll come over here, and there'll be a module right here, and here comes L2 right here, right? You understand? And then they'll run L2 from over here, and then right next to it is another L2, and they'll run this L2 from over here somewhere. When they should have done what? They should have just put a little jumper right there, right? You understand? So here I'm trying to trace L2, and I come down here and hit this, and I'm supposed to go 4 different places. And then I look up here, and there's a jumper that goes here, back over here, and then there's another L2 beside it, but it's coming from over here, right? You understand? So what I recommend you do right off the bat when you start wiring is to wire the L2 side, and you should be able to do it just like this. Y'all understand that? So I should be able, if I've got a device, let's say I've got a relay right here. I've got a relay right here, and then I got something else down here. I got something else down here. I can bring L2 to right there. Then I can put a jumper and take it right there. Then I can take a jumper and take it right there. Right? You understand that? And so now when I'm tracing, I can start on L2. I can come down here at the first one. I can go to the second one. I can go to the second one. Right? You understand? It makes it real easy for me to trace L2. And you should do the same thing to L1. So L1, we got all these push buttons and stuff over here and all these sensors and stuff over here. Well, what you should do, instead of trying to run them all the way up here, you should bring down L1 and do what? And jump it like that too. And notice you'll never ever get more than 2. You'll never ever have more than 2 wires. Never. And things that are beside each other, and that's what I recommend, is I recommend to start off, you do what? Run L2, run L1, and then hook up between. And that way you can see the way you run L1. You can see the shortest path. So what most people is doing, you're doing rung per run. You're wiring one rung up, and then you're down here and you say, I need L2. Normal tendency is to say, well, L2 is up here on my transformer, right? So you go up there and do what? You hook up there. And then you come back and you say, well, Rich says we can't have more than 2, so let's find an L2 somewhere. And you just hook it what? Somewhere, instead of doing it real logical. So now, normally when it says how do you check your wiring, y'all know I'm not checking the wiring of your circuit. What am I checking? I'm checking L2. Because if L2 goes where it's supposed to, you cannot have a short circuit. If L2 does not go where it goes to, then you either don't have something hooked up, if you got it hooked up in the wrong way, right? Understand? And that's a normal tendency too, where people get what? They'll get L2 and L1 confused with each other. Especially on our motor controls, because we got L1, L2, L3 3-phase, 208 volts, and then we got what we call L1 and L2 single phase over after our transformer, right? You understand? Motor controls, you get somebody to screw that up every time. They say, I got to hook this up to L1 and they'll hook it up on the output of the disconnect, right? And then another tendency we have is to get L1 and L2 confused inside your diagram. You say we need power. You get what? You get X. So the outputs of the transformers are not labeled L1 and L2. They're labeled on the primary, the secondary side are X's. The primary side is what? H's. Or I'm sorry. The high voltage side is H's. The low voltage side is X. In some transformers, you can hook them up backwards. So not backwards. You can bring your input into the low voltage side, and then you get a step up transformer, right? So you can either step it up or you can step it down, depending on which one you use as a transformer. So on transformers, if they're not ones you get from Radio Shack, they'll normally label primary and secondary. Industrial transformers, they label them high side and low side. You know, why do they label high side? H, how do they label the low side? Yeah. And you might have multiple high sides and you might have multiple low sides depending on whether you got a multi-winding secondary or a multi-winding primary. So our transformers, we have a multi-winding primary, but they've already wired it to go to divide by 2, right? You understand that? Remember, in motor controls, you had to do what? You had to wire, but we're past that. Also, our motors are already wired for low voltage. If we wanted to rewire them, we'd have to pull that panel off the side and rewire them. That's the way you would actually have to do in the industry, right? You understand that? You know, one day we'll pull. Well, I'll do that when y'all go back to the lab. I'll pull the cover off this motor right here, and you can actually see the terminals in there where you would have to rewire the motor for what? High voltage or low voltage. Of course, in motor controls, we bring all that out to these banana plugs so you can do it that way. But I'd like for you to see exactly how it's done. But isn't it neat, those metal tabs, and all you do is you move them, and that's why they cross that's why they cross those things, because you can move those metal tabs because you never have crossing, right? So you can wire or divide by 4, divide by 2, just putting those metal tabs between the right. So if I wanted to wire, y'all know what I'm talking about? Yes, no. Yeah, but if we look at the wiring diagram, it's so strange, and people want to know why they do it that way. Why do they cross those leads? So if I look at the wiring diagram, it comes over here and it looks like that. But what they'll do is this guy here is crossed with that guy right there. So this is H1, this is H2, this is H3, and this is H4. So we always bring our power in on H1 and H2. Well, the way the thing is laid out, if I want to wire it for high voltage, I'd put that metal jumper right here, right? You understand? If I wanted to wire for low voltage, I'd put my metal jumpers between here. So what we can do instead of me actually putting physical wires, I can just take those little metal tabs that comes with the transformer and just move them, right? And set my ratio. So usually when you buy a multi-voltage transformers, they'll have those little tabs in there with it. And that's why they cross what? They cross X3 and X2. So if I wanted to wire for high voltage, I'd put my jumper between what? X3 and X2. If I wanted to run low voltage, I'd put my jumper between H1 and H3 and H2 and H4. And that's the way, if you look at ours, you see that metal tab. It's between what? H1 and H3 and H2 and H4. And that's why they cross them like that. Just put what? Just put those tabs up there. All right, that's the phone check. So how many wires on the transformer? Yeah, just L1 and L2. And do all your jumping out there in Okay, so what do you want the on delay to do?
The time.
That is not the symbol for a timer. That's the symbol for a timer. That's the symbol for a light. You don't need this rung. For some reason, you added 2 red buttons. This is your timer. This is your red light. That rung is not supposed to be there. You're just trying to figure out how you could jump out this guy and this guy with a push button. That's your red light right there. Right? Okay. Understand? This is your timer. This is your red light. So what you're doing is when this contact right here closes, your timer starts timing. After 10 seconds, this guy turns up and the red light goes off, which you're supposed to do. What you're trying to do is figure out how I can turn on that red light with a push button, but you added a light with a push button on it, and that's not what I'm saying. I said you got to figure out a way you can jump this guy. So if you're going to turn on that red light some way, your push button's got to jump over this guy, and it's got to jump over that guy. So where's that push button going to be? So how in the world would that turn on the red light? I don't know how else I can say it. Your push button has got to jump over this guy, and it's got to jump over that guy. Mm-hmm. Your push button's got to jump over this guy and jump over. So let's say I come over and put it right there, and this contact right here is open. How would that turn on the red light?
It won't.
Okay, I want a push button that jumps over this guy and that guy right there. So where are you going to put your push button at? I don't know how else I can say this there. I just don't understand. I don't see why you don't see that. Well, let's see. What if I came over here and put my push button? I come over and put it right there. I come over here and put my push button right there. I jump over that and I put it right there. Now, when I press that button, would the red light come on?
Yeah.
Okay. Would I jump over this? If this was made, would the red light come on?
Yeah.
If this was turned off, would the red light come on?
Yeah.
Okay, so could I use that as a push for test right there?
Yeah.
Okay. So why couldn't you see that? So why was you trying to put it in here? If I put it over here, I'm not jump. I might. You understand what I'm saying?
Mm.
So there's your push test right there. I did that for you. So CRR. I'm gonna put my name in.
Okay.
So this is why I can't understand. You know, I don't. How else would I have phrased that? Tell me what I should have said for you to see that push button jumping over those two
Jump
guys.
over.
There.
That's where I should have caught on.
Well, what you got to do is say, I need, if I'm going to turn, so here to turn on that light, you put a direct path through the push button to the red light. Except what you did is you stuck another red light in there, right? And you call this a timer and you call that a timer. Even though you draw it and that's not the symbol for a light. Y'all got to start doing these industry standard symbols. If I look at the symbol for a light, it's 4 lines right here and then my signal comes in. That's the symbol for a light. This is not a symbol for a light. Right? Understand.
All right. So this is my red light right
That's your red light. That's what it was yet. That's what it was last class. And for some reason,
because I thought I had to add another rung.
why? All you need to do is have a direct path to turn on the red light, to jump over all this stuff because it's a push to what? It's a push to test. When you push to test, the red light's supposed to come on no matter what. Now, of course, if it's already on, you can push that from now to doomsday and nothing's going to happen. Would this bring in that? No, it's not going to bring in that. It's a push to test, right? You understand that? Yes or no?
Yes, sir. Because
A
I'm
lot
testing
of
the red light to make sure it comes on.
To make sure, because the red light says stop. So if you lose the red light on a traffic light, that's a problem.
Yeah.
If you lose the green light, it's not near as big. The red light never comes on. So that's one of the reasons they're going from light bulbs to LEDs. Because you can lose a couple of LEDs and still work if you lose a light bulb. A lot of your traffic lights are doing that.
So I eliminate this rung right here.
Yeah, and you put the right symbol right here. This is the wrong symbol right here. So right now when I grade that, that's the wrong symbol. That's not the right symbol. So that's what I'm gonna start. Y'all listen up. When I start grading these diagrams, they're gonna have to be the industry standard, right? They're gonna have to use the right symbols for all these sensors. So if you use the wrong symbol, then you're gonna get marks on this, right? Everybody understand that? So I'm gonna give you a chance to go back and use industry standard symbols. If you can find that symbol right there in the symbol chart, I'll give you credit for it.
Because I got it off that.
No, you didn't get it over. I don't know where you got it from.
Never put them symbols on them panels.
Okay, so when and so they do on motor controls. I like this, they don't, because you're not gonna go out there and go to work for US Steel and go in there and see a relay and have the symbol for the relay on there, right? But you've already had motor control, right?
Well,
And if you don't know it, guess what I've got up on Blackboard for y'all?
I know where to get it. I think
Yeah, I should have them up here.
I don't think it's right. I think. Oh, before I turn this into use, I'm gonna take it.
I think
Well,
if they're not up there, they should be. That's what I'm checking now to make sure those symbols are up there. If they're not, then I'll put them up there.
well, I went back to one of our other classes. Some of it, but they're in the back of the big motor control.
Here, yeah, they are. I know. So here's our proximity switches right here. Now if it's a 3-wire sensor, you're gonna have to add the power wire, right? One to L2. Okay, are you using normally open or are you using normal closed? Not normal closed, normal open. You should know that. So this is the symbol for a solid. This is the symbol for proximity. So let's see. Show. Let's see. Does it have a temperature?
Are those?
I'm gonna have to find, oh, so here's a temp switch, so that's the symbol I used a while ago. Here's a float switch, so when you start doing your level control, this is the symbol you should use. This is a pressure switch, right? This is a proximity switch. This is a flow switch. This is a foot switch. So we're not using those. So if it's a light sensor, you have to figure out if it's either normally closed or normally open. Then on a photo sensor, you got to add a wire coming out the pipe going over to L2. And where's this at?
Where is that?
On Blackboard. Inside what?
Some here, but they don't look like those.
And,
I think they do, it's not the same.
Yeah, inside handouts. And then there's electrical, I should put symbols up there. So I do have the thing labeled wrong.
You have these off of one of your class. I think I got the. Oh, you took it down. You took it down.
Yeah, I was trying to relabel it. I got electrical sensors on there when it actually should be called electrical symbols. When I put the title up there.
Before we turn the video off. I think I'm looking at it. I started with it right here. Right out, but, let's get in. Yeah, everything you need.
We'll do that next time. I still hadn't found my solid state sensor. Oh, here it is.
so this is where I got this number from.
Okay.
That's why I put it in my diagram.
Well, no, you put even that, you drew it. Where's your diagram? If those symbols are the same, Eric, I'll give you $100. So what's that a symbol for? If you think those symbols are the
No.
same,
I had them right here.
no, yeah, but this, look at this symbol right here. We call this a triangle.
Mhm.
We call this a diamond, right? So this is a square. Is that a square?
No.
Okay, so even if you had it like that, it's still not the right symbol, right? Understand?
Yeah.
So see the way you did yours?
That's a triangle. This is
Yeah. And it's just a square, but it's offset. That's all it is. It's a square. So that's the symbol right there. And that's the symbol that I've been using in class, right? So that symbol right there would be okay. I can understand that, but it's still the wrong symbol, right? Yes, no?
Yes, sir.
All right. Yeah, just hold on a second. I'm trying to find something I can. So we should be able, with this sensor, we should be able to measure the temperature.
better place.
Okay, guys, this is the circuit. Very simple circuit. So what I've done is I brought 5 volts into VS. I get this connected to common. I've got my output of my meter connected to my output. I measured, it's 10 millivolts. Y'all listen. It's 10 millivolts per degree Fahrenheit. So what's the temperature?
Probably about 110 degrees.
No, it's not. Yeah, it's real easy. 10 millivolts, right? You understand. So all I need to do is just move this right here. And it'd be 83, almost 83 degrees. So if I touch it, it should go what? You'll see that?
Going up to 98.
Well, it won't get that far because it's my fingers. Your fingers, the tips of your fingers, if I put it in my tongue.
It's going up.
So it wouldn't surprise me if this is not what's in a digital thermometer, because it's really, really easy to do. All I'd have to do on my display is just move my decimal point over, right? Just move it over. Power this thing up on a battery, right? Understand that? Very, very accurate too. So this is the solid state sensor. Anybody got a digital thermometer in your house? When you stick it under your tongue, you measure. You don't.